Hey, what's up? My name is JC and I'm an instrumentation technician. And welcome to AutoCal Tech. And today we're going to look at the top two temperature sensors, the RTD and the thermocouple, and how they work. Specifically, we're going to look at how to measure and how to source back to the DCS so you can feel comfortable knowing how to do that whenever you're in that situation. Later on in this video, also, I got an RTD here, and it could be made out of platinum, it could be made out of nickel. I'm not even sure, to be honest, but we're gonna be able to find out together. We're gonna test it out using a meter. It's a 3-wire RTD. We're gonna be attaching to all three. And what we're gonna be using is Fluke 789, just switching it to ohms. And we'll do that together later on in this video, so let's go. Okay, so thermocouples, let's go and talk about them. We're gonna talk about the working principle, how do they work, and then we're gonna compare that to the RTDs, work through RTDs, how to measure and how to source. And so here we have just a simple drawing here. Got a thermocouple inserted to a tank, and you got red and yellow. So this is a type K thermocouple generating its own voltage, right? So from the DC or from the RIE, you have no voltage going to the thermocouple itself is generating its own voltage. And here in a little bit, we're going to talk about how that does it and how that voltage is actually being produced, right? Of course, in here, there's the J box, the RIE. In here, you can also have the transmitter anywhere between here or here. So let's keep going. The next slide's kind of important here. Okay, perfect. So a couple things that I want to point out is you have two sides here, right? So you have the measuring junction, which is here, and then you have a cold junction. So the measuring, sometimes that's called the sensing junction or the hot junction. This is usually called the reference junction or the cold junction. But basically what that's talking about is the measuring junction is the end to where the probe is actually inserted and actually being exposed to the heat, right? So the alumel and the chromel type K thermocouple, and I've used type K simply because it's the most common that I've seen. I'd like to speak for every industry, but I can't do that. Nonetheless, alumel here is the negatively charged or the negative wire, and chromel is the positive. But at the very end of this probe is where it's actually joined, right? Two dissimilar metals or two different metals joined together that will generate a voltage proportional to the temperature to where the probe is actually exposed to. Okay, so I just want to point out you got the measuring junction and the cold junction, right? So, okay, so the working principle, how does a thermocouple actually work? Skip the spot. All right, here we go. So it uses something called the Seebeck effect. So if we go to here to number 4, now let's reference number 1 here. We do not need a power source that generates its own voltage. I know I said that, but going back to number 4, the Seebeck effect, where two junctions of a thermocouple at two different temperatures will generate its own potential voltage, right? So what that's talking about is this part right here, the end, and this side right here are at two totally different temperatures. Okay, so this is actually inserted into the tank or the pipe or wherever it's actually inserted into. And this cold junction could be in, let's say it's ambient temperature. It's going to be totally different temperatures. So using the Seebeck effect, what that's talking about, what that is whenever we apply heat to this end of the probe, this wire, this metal alloy, and this metal alloy or this wire will have electrons moving in here. Okay, and the amount that it'll move will be dependent on the amount of temperature that the probe is actually exposed. So this chromel will have electrons moving, and it's always going to move from the hot side to the cold side, right? So this measuring is the hot, the cold junction is the cold side. So you're going to have electrons moving from here and basically pushing this way to the right side. So you're going to have electrons moving this way, and the same thing is going to be moving. The same thing is going to be happening on the alumel side, the red wire. So you have electrons moving on in this metal alloy, same here, but since they're two different metals, you're going to have two different amounts of electrons being pushed over to the cold side. And because there are two different types of electron or two amount of electrons being pushed to the cold side due to the different alloy, you're going to have a, a potential difference across these two here. So you're going to have X amount of electrons moving to the cold side, and this alloy, this one, the, the amount that's in the positive side minus the negative side is going to be equal to a potential difference or potential charge, where we know a potential difference, we're talking about voltage, right? So if you were to measure with a voltage meter from a negative to a positive, it's positive minus your negative, and that's going to equal your voltage, right? So, and we can kind of create another video later on about that. But nonetheless, you're going to have electrons moving this way and electrons moving this way, and you're going to have more electrons moving on the negative side. So you're going to have more on this side here, which is why this red wire is the negative side, which is this wire is using aluminum, and why it's the more negatively charged wire. So let's keep going here, and we see here how we can check just using the voltage. Now, this is using, you can use this, whichever type of meter you have, but nonetheless, we're checking voltage. Now, we're not checking just normal voltage, we're checking a very small voltage, right? So it's going to be low signals applied from this thermocouple. So we have millivolts. That's actually a millivolt reading that can actually be translated to a certain temperature for type K. Okay, so let's look at RTDs here. So RTD is a temperature sensor that increases in resistance as the temperature and the sensor increases, or vice versa. RTDs will be available in 2, 3, and 4 wire configurations, although what I've seen mostly of is the 3 wire. The higher the temperature exposed to the sensor, the higher the resistance will be, also known as a positive coefficient. But that's just a fancy way of saying that the higher the temperature, the higher the resistance. And that's all that means here. So just a couple, just a simple drawing here of the configuration between a 2, 3, and a 4 wire. I want to hone in on this 3 wire RTD here. You got two reds here, which is the common side, the resistor, and then the non-common side, right? So I'm going to refer to this as the common side here. And here is just a symbol. That's an actual schematic symbol here of a variable resistor. So how to measure a 3 wire RTD? Okay, so let's say you got an RTD here. You need to do a PM or a preventive maintenance on this 3 wire RTD. So how do you do this? This is not a 789 meter. This is a 724 meter fluke meter that I have in my toolbox at work, and super helpful. But nonetheless, here you simply just click on measure, click on that RTD until you know which RTD you have. Let's say you have 100 platinum ohm RTD. Okay, so the black is the common. The next one would be the red, and then the one across right here needs to be also with your common. So lead here, these two diagonals here will go to the common side, and the one right above the common, jack, will go to the non-common side. This will effectively be used to be able to measure a 3 wire RTD. Simple as that. How to measure a 4 wire RTD. Let's say you got a 4 wire RTD in front of you. How do you measure that? Let's just go through that real quick. So you got a 4 wire RTD. Okay, so basically doing the same thing. You got your common here. This can go on either side. Now you got a 4 wire RTD, but let's just go to the red. So on this black here, goes to the red. The one diagonal to it goes to the same side. Okay, now the one right above the common, this one right here, goes to the to the white, and the one diagonal to that one gets joined up with the other white one, right? So it's just a crisscross, right? So the black one will go to the black jack will go to the red, or the black lead will go to the red. The jack diagonal to it will also be connected to that red as well, and vice versa with the white wires. Awesome. So what I have here is basically just a transmitter. This is a 3144 roast mount transmitter, just a simple little drawing. You got your power wires here, which also sends a 4 to 20 milliamp output to the DCS. And what I want to point out is just something real quick for you to remember. If you're gonna source a 3-wire, or you're gonna source any RTD, what I want you to do, if you're using the 724, I want you to remember stack to source, right? Stack to source. So if you're going to source, you need to stack the leads, and this is simply what's worked for me, right? So that's what I want to teach you. For the black one here will be, you got a black lead first, or I'm sorry, yeah, black lead first. And I probably should have painted this red one here, but nonetheless, you got a red lead stacked on top of the black, and those two will be joined up on number 2 and number 3. The one above that will then go to number 1. Now, you can always, if you look in the back of the lid of any transmitter, or specifically this transmitter, it'll tell you that what we have here, right, you got the non-common resistor, and then the common and common. It's basically referring to what we're doing here. We got the common and the common resistor, non-common. So on that transmitter, we got number 1, number 2, and number 3. Right? So number 1, number 2, and number 3. So this transmitter inside of it is configured in a certain way to where it can use this meter to be able to receive its input from the meter, will then be translated or converted or transduced into a certain milliamp output to the DCS, right? So different from the measuring side, on the 724, you simply click the source, the same thing, RTD to the specific RTD that you're working with, and then just following up to stack to source, you are then able to source to the transmitter, and instead of using the RTD, you can source from the transmitter all the way back to the DCS. And that's how you can source a 3-wire RTD. Okay, so we got an RTD here that we're going to see whether it's made out of nickel, made out of platinum, see what this element is made out of. The first thing we're going to do is, with our leads here, we'll switch over to ohms, and we'll just do a simple ohm check. All we're going to do is we're going to go from red to red, and we should have a low ohm reading, which we do. That's great. Now, got a 0.9 right there. Now, keeping this one here in the red, we're going to hook up to the white to red, and we got 112.2 ohms, right? So the higher the resistance, the higher the temperature. I know right now where we're at, it's about 85 degrees right now. Now, if we switch this one here, which is a red, we're going to keep this one on the white. Let's go ahead and switch up to the other red. It should have the same reading right there, 112.2. Great. So using that ohm reading, we can go to reference an RTD resistance chart and see exactly what kind of element we have here, what kind of RTD we have here. All right, so we're still hooked up here. We're just going to test it out. We're going to check out this ohms reading, and we're just going to put a flame on this temperature element here. And we're going to see, so you can see that ohm reading there going up as you're applying a temperature on that element there. We got 188, 192. So let's go to take that off. and that should start cooling down. And really, using that 112 ohm starting point, we can reference that chart and we can see how high we actually went and see how hot we actually went on that temperature element. So let's go and check that out. Okay, so earlier we were looking at the RTD and we got about 112.5 to 112.8 ohms. And what I have here is just a cross-reference check of chart for RTDs. This is only specific for the 100 ohm platinum RTDs. And yeah, let's look through there. Let's look for the 112 and see how much temperature. I know where I'm at right now, it's about 85 degrees-ish. So there is 112.5, 112.7. Okay, so I'm going to 112.5. It's telling me to in the 80s, the upper 80s, which I definitely believe that. Now, let's look at some other configurations real quick. That's probably what we're looking at, the 100 ohm platinum RTD, which is really common, probably the most common RTD that I've worked on. Now here's a 120 ohm nickel RTD that I've pulled up. We're going to look for the ohms of the 112.5. Here I got, oh, that's 102. Here 112.62. This is telling me it's if that were true, it'd be 10 degrees Fahrenheit. And I'm wearing a t-shirt. Ain't no way that's 10 degrees Fahrenheit here. So what we're thinking is that RTD that we're looking at, just using this resistance cross-reference chart, that this is RTD is a 100 ohm platinum RTD. We checked 112.5. It's in upper 80s. That sounds about right. All right, so in this video, we talked about the two temperature sensors, the RTD and the thermocouple. We talked about how to measure and how to source. So if you got any value out of this video, please hit that subscribe button, the like button, and we'll see you in that next video. Thanks.